Hello friends, my name is Mohsin Mullah and I welcome you all to this video lecture. In this video lecture, we are going to see about the conditions at which the optimal operation can be obtained when there are a number of units operating in a particular area in a region. Suppose there are n number of generators operating in a particular area. So in that case, what we can do is we can try to obtain you can say optimum condition for their operation so that the overall cost of the total operation is less. Suppose the individual units of this particular plant are generating values like pg1, pg2, pg3, so on up to pg1, pgn, and this plant is generating these different outputs by the different units is to meet a particular load demand, which is indicated as PD. And from our previous discussion we know that the cost for each of the plant can be obtained as the cost for uh, fuel cost for first plant C1 of Pg1 can be written as A plus B Pg1 plus C Pg1 square. Similarly, the cost for the second plant can be written as here C2 of Pg2 equal to A plus B Pg2 plus C of Pg2 square. Similarly, we can obtain C3 of Pg3 as A plus B Pg3 plus C into Pg3 square. Okay, so like this we can write for the nth unit, the cost of nth generating unit can be written as Cn of Pgn equal to A plus B of Pgn plus C into Pgn square. Okay, so like this we can try to write, and we can finally write all these values as a summation also, because this is for a particular area. So the total generation, or you can say the total demand, can be met by this total generation, so the total cost will be for a particular area. So therefore we can write C equal to as a summation between I equal to 1 to n Ci of Pgi. Okay, so we can write this. Now for the optimum operation of the plant consisting of number of units, we need to determine a optimum condition. So that optimum condition is nothing but to minimize the cost of generation. So we have to try to minimize this cost of generation. So here to minimize the cost of this generation, it is not as simple because there are some constraint also. Okay, so there are constraint in this optimum you can say generation situation. What are those constraints? Let us try to see. The constraints are very important here. Okay, so let us just try to write the constraints. So the very basic constraint is that each of the generator is going to generate within a particular limit. Okay, so suppose ith generator is going to generate in a particular limit of Pg minimum to Pg maximum. Okay, so it has to meet this particular requirement. It cannot generate less than the Pg minimum value, and it cannot generate more than its maximum capacity. Okay, so that condition needs to be satisfied. And also there is another condition, is that whatever that generation we are going to do, that summation of I equal to 1 to n Pgi, total generated value, this should be equal to greater than PD in usual case. But since here we are not going to consider the reserve capacity, so directly we can take this as, or we can just try to say that this summation should be or generated value should be equal to the demand. It should be exactly equal to the demand. So this condition should be satisfied, and with these constraints we should try to, we need to minimize the earlier value of C, minimize C, so which is nothing but I equal to 1 to n Ci of Pgi. Okay, so with these constraints we have to somehow manage to bring down the value of C. Okay, So now to do this, there are different techniques. One of the techniques is to use the Lagrangian solution. So here we will use the Lagrangian, we will employ Lagrangian technique. Okay, so in this situation, because there is a function also and there is a constraint also, so in such situation that Lagrangian function or Lagrangian technique to minimize the function will be most suitable. Okay, so now let us try to see what exactly is that Lagrangian function and how it is used to get the minimal condition for a particular function. So suppose there is a function f of x given by, okay, this is for example here, let us just try to understand. F of x is a function which is given as x square plus y square, and there is a condition. Okay, so there is a satisfactory condition that is given as satisfactory condition is that we have to satisfy this condition, x plus y is equal to say 10. Okay, so we need to satisfy as well as this is the function. So now so we have to try to get a new function in terms of the Lagrangian function. So let us now write new function. Let us write a new function, write a new function in terms of Lagrangian function. Okay, so which will include that satisfactory condition also. Okay, so that is basically represented as here L. So L of say this function is for different variables, so there are x, y, and we'll take one multiplier called as lambda. Okay, Lagrangian multiplier lambda. So this can be this particular new function is represented for the given function f of x only. So this new function is equals to f of x, but along with that there will be one term plus or minus lambda into g. Okay, so now here what is that g? Now this g is the that equality condition, or you can say compulsory condition that we need to satisfy. So that is necessary condition to be satisfied. So here g is nothing but, we can say this is nothing but x plus y minus 10. Okay, so that is the condition, this is equal to 0. Okay, so now therefore we can try to write this Lagrangian function x y lambda equal to f of x. So here we have a choice to either select a negative or a positive sign for this particular writing the expression here. Okay, so let us try to use that sign of you can say plus. So let us see what expression we are going to get from here. So therefore I'm going to use this plus sign, and here this is lambda times g is nothing but we have written this x plus y minus 10. Okay, so now to get the optimal condition, so we have to do the partial differentiation. So we have to perform the partial differentiation of this. So therefore partial differentiations can be obtained with respect to each of the three variables that we have listed here. Okay, so partial differentiation is obtained. Okay, so dou of L divided by dou x, dou of L divided by dou of L divided by dou y, and dou of L divided by dou lambda. So when we do that partial differentiation, we will be getting some three equations, solving which we will be able to determine the values of x, y, and lambda, which will satisfy the economic condition or that optimal condition. So now let us do that partial differentiation. Therefore, so let me just say this is equation number 1. From equation 1 we get, so when you do the partial differentiation with respect to each of these terms, so I'll just write the first one, dou L by dou x. So differentiation of this expression with respect to uh, dou x will be equal to so f of x is already given here earlier, so let us just try to substitute this f of x first, then we can do the partial differentiation. So here first let me just or here we can change here. So this is x square plus y square, because already it is given as f of x is s square plus y square. So after that only we will do the differentiation. So therefore here it will be 2x plus lambda. This will be equation number 1, and this has to be equated to 0 basically. So let us just try to write equal to 0, and this is equation number 1. Similarly we can obtain dou L by dou y equal to 2y plus lambda equal to 0, that is equation number 2. Similarly dou L by dou lambda, that will be equal to here x plus y, okay, minus 10 as it is into 1. So therefore this is what we are going to get, and this is equal to 0 again. This is equation number 3. So solving equation 1, or you can say this is equation number 2, equation number 3, equation number 4. Solving equation 2, 3 and 4, we get the values of x, y and lambda, for which the given function is optimum. The given function f of x is optimum. Okay, so now let us use this technique on the given our function, that is for the cost whatever we have written, that is c equal to summation of I equal to, now we have c equal to summation of I equal to 1 to n ci pgi. Okay, so therefore this is having one condition, with condition summation of I equal to 1 to n pgi equal to pd, or we can write this as g, and this g is nothing but summation of I equal to 1 to n pgi minus pd equal to 0. Okay, so now we have to use this condition also in the that optimal equation. So therefore let us write the new function in terms of, so these words are not required, just for your reference I am writing in terms of Lagrangian function. So L, so I'll not write the that functional form L of, so directly you can understand this is the function of the variables available in this given function. So therefore let us just try to write the expression here. So this is basically the given function times I equal to 1 to n f of x plus or minus lambda, right, that we had written. So sorry, ci pgi plus or minus lambda times, other condition is that lambda into that summation of I equal to 1 to n pgi minus pd. Okay, so this is what the condition is. So instead of using the both plus or minus, we can choose any one sign. So let us choose the negative sign here. Okay, so it doesn't make any difference, only the, you can say whatever solution we are going to obtain, the sign of that will change. So here let us take minus sin lambda times pd. Okay, now this is what the condition is. Okay, so similarly we can try to obtain for a particular unit. Okay, so we will try to obtain this function for a particular unit here. So say for kth unit, kth unit, Lk can be written, and for kth unit the cost will be Ck Pgk, okay, plus the remaining units I equal to 1 to n, where I is not equal to k, Ci Pgi, okay, and remaining term will also follow the same summation. So first term will be for the that kth unit, so it will be Pgk plus summation I equal to 1 to n, where I is not equal to k, Pgi minus Pd. Okay, so this is what we are going to get. Okay, so now to obtain the optimal condition, we have to differentiate this. Differentiating with respect to the generating value of that particular generator k, differentiating with respect to Pgk, we get dou Lk by dou of Pgk equal to, so here Pgk directly we can substitute in terms of that expression we already know, which is nothing but this is Ck of Pgk. So Ck of Pgk is nothing but already that condition we had obtained, a plus b Pgk plus c Pgk square plus summation of I equal to 1 to n Ci Pgi minus lambda times Pgk plus summation I equal to 1 to n Pgi minus Pd. Okay, now differentiation of this will be equal to, this is still I'll just write this as Lk only. Okay, so now let us write the differential term. So this will be equal to b plus 2c Pgk plus here there is no kth term, so therefore this term is going to be 0 minus lambda times the first term is 1 plus here also there is no kth term, 0 minus 0. So therefore here we can write dou Lk divided by dou Pgk equal to b plus 2c Pgk minus lambda equal to 0. This should be equal to 0, or lambda equal to b plus 2c Pgk. So similarly we can try it for the some other term, so say mth term. Similarly for mth unit we can write, so we will get the same type of equation for mth unit as well, and when we do the differentiation of that, so we are going to get the similar type of expression. So you can see that for mth unit we can write this as a plus b, here it will become Pgm plus c Pgm plus summation again I equal to 1 to n, I is not equal to m, Ci Pgi minus lambda times Pgm plus summation I equals to 1 to n, I is not equal to m, Pgi minus Pd. So differentiating this we are going to get dou Lm by dou Pgm is gonna be, again it is going to be b plus 2c pgm minus lambda equal to 0, or lambda equals to b plus 2c pgm. Okay, so likewise for any of the term we are going to get the similar kind of expression. So what it indicates is that, so when we are trying to obtain the optimal value of the particular unit, so that incremental cost, so this lambda is nothing but the incremental cost, so ultimately the incremental cost of that unit is going to remain exactly same. So therefore what we can write is from this particular form, so this basically del equal to b plus 2c pgi. So I can generally write for ith term is called as coordination equation. Coordination equation, and this indicates incremental cost, and this basically indicates the incremental cost. And for optimal operation we already know that the incremental cost should be same. Incremental optimal operation, lambda should be equal to 2 plus 2c pgk, that should be equal to b plus 2c pg m, that should be equal to, or you can generally write this as 1 here 2 so on equal to b plus 2c pg k, or any other term you want to write. So as many generating term you can say units are there, so you can write up to nth unit also. Okay, so this is the condition for economic operation of the plant containing a number of units. Okay, so we'll see one example on this in the next video lecture. Till then, happy learning and thank you.